Hello students, today we shall begin with unimolecular surface reaction. Surface reactions involving single adsorbed molecules and therefore classified as unimolecular are treated in terms of Langmuir adsorption isotherm. The rate is proportional to the fraction theta of the surface that is covered by the molecules. Here rate will be equal to the constant K into the fraction of the molecules which is going to be adsorbed, that is theta, and that will be equal to K into concentration of A with its constant divided by 1 plus K into concentration of A. The dependence of concentration of A is given in the next slide. At sufficiently high concentration of A, the rate is independent of concentration, which means the kinetics are of zero order. Now this is going to be a graph representing between the rate of adsorption and the concentration of the molecules. The first figure is going to be a unimolecular adsorption which represents Langmuir adsorption isotherm. That is, at higher concentration it is following zero order kinetics. And the second two, B and C, are going to be the graph which is represented for a bimolecular reaction. Bimolecular reaction can take place by two mechanisms, that is Langmuir-Hinsel mechanism and Langmuir-Riedel mechanism. So in case of unimolecular reaction, when the concentration of A is much lesser than 1, the kinetics is going to be of first order. Here some of the examples of this is going to be the decomposition of ammonia on tungsten and decomposition of phosphine on glass. In case of unimolecular reactions, when we are going to consider an inhibition, that is when substances other than the reactant is adsorbed on the surface, with the result that the effective surface area and therefore the rate of adsorption is reduced. Suppose the substrate A is undergoing a unimolecular reaction and on the surface, and that a non-reacting substrate I is known as an inhibitor or a poison is also adsorbed. Then the fraction of the molecule covered by A is given as theta is equal to K into concentration of A divided by 1 plus Ka into concentration of A plus Ki into concentration of the inhibitor I. Ka and Ki are the adsorption constants of the molecule A and the inhibitor I. Then the rate of the reaction is will be given as V is equal to K theta, which is going to be adsorbed on the surface, which will be equal to K into Ka into concentration of A divided by 1 plus Ka into concentration of A plus Ki into concentration of I. In the absence of inhibitor, the equation reduces to the Langmuir adsorption isotherm, that is K theta Ka into A divided by Ki into I. This behavior arises from the fact that since the surface is spatially covered by A, the coverage is proportional to the concentration of A, and since it is covered almost fully by the bare fraction is inversely proportional to the inhibitor I. An example of such reaction is going to be decomposition of ammonia on platinum, which is inhibited by hydrogen. In this case, the rate equation is given as V is equal to K into concentration of ammonia by concentration of hydrogen. Since hydrogen is a product of the reaction and there is a progressive inhibition as reaction progresses. Coming to the bimolecular reactions, wherein there are two different mechanisms when the molecules of the two reactants A and B are adsorbed. One is Langmuir-Hinsel mechanism, where both A and B are adsorbed on the surface. Another is Langmuir-Riedel mechanism, where one of the molecule is adsorbed and reacts with the molecule in gaseous phase, and the kinetic equation for both of these are different. Coming to Langmuir-Hinsel mechanism, wherein the reaction is considered between two adsorbed molecules. Here the rate is proportional to the fraction of the molecules adsorbed by both A and B, and rate will be equal to K into the product of the fraction adsorbed by both A and B, which is equal to K into Kb into concentration of A and B divided by 1 plus Ka into concentration of A plus Kb into concentration of B square. If B is held constant and A is varies in accordance in the figure which is been observed previously, the rate first increases, then passes through a maximum, finally decreases. The rate falls at higher concentration is that one reactant displaces the other as concentration is increased. Coming to the reaction between two adsorbed molecules, the maximum rate corresponds to the existence of maximum number of molecules in the neighboring AB pairs. Considering the case where sparsely covered by surface of both A and B, that is the concentration are low, that is Ka into concentration of A and Kb into concentration of B may be neglected in comparison to unity, then the rate becomes V will be equal to Ka into Kb into concentration of A and B, and this is following second order kinetics being first order in both A and B. Coming to another case when one reactant is weakly adsorbed. If reactant A is weakly adsorbed, then Ka into concentration of A in the denominator is neglected and the rate becomes V is equal to Ka into Kb into concentration of A and B. As we have neglected Ka into A, 1 at the denominator 1 plus Kb into concentration of B whole square. The rate still passes through a maximum as B is increasing. As long as Ka is much less than 1 plus Kb into B remains satisfied, the rate is proportional to A. Reactions involving where one reactant is weakly adsorbed, continuing it is observed in reaction between hydrogen and carbon monoxide on platinum. If reactant B is adsorbed sufficiently stronger, Kb into concentration of B is much greater than 1, then rate becomes V is equal to Ka into A. The rate is inversely proportional to B and the order with respect to B is -1. This behavior is observed in reaction between carbon monoxide and oxygen on quartz and on platinum. In both the cases, rate is inversely proportional to the pressure of carbon monoxide, which must be strongly adsorbed. Coming to the case where reactant between a gas molecule and an adsorbed molecule, which is going to follow Langmuir-Riedel mechanism. In this case, the reaction occurs between adsorbed B molecule and a molecule of A which is in gaseous phase. Then the fraction covered by the surface B is given as theta B, Kb into B divided by 1 plus K into concentration of A plus Kb into concentration of B. And the rate is not proportional to the fraction and to the concentration of A. So the rate will be equal to K into the fraction of the molecules adsorbed by B into concentration of A, which is going to be given. There are not many reactions occurring by this mechanism. The reaction between ethylene and hydrogen appears to occur under certain circumstances by Langmuir-Hinsel and Langmuir-Riedel mechanism occurring side by side. Coming to the case where adsorption of two gases without mutual displacement. In such case, Langmuir isotherm for adsorption of molecule A is going to be of type 1 and for adsorption of B on the site is going to be of type 2. Here theta A is equal to Ka into A divided by 1 plus Ka into A and fraction of molecules adsorbed by B is equal to Kb into concentration of B by 1 plus Kb into concentration of B. Since here both are not going to mutually displace each other, the rate is proportional to theta A into theta B and thus the rate expression will be equal to K will be equal to V is equal to K into Ka into Kb into concentration of A and B divided by 1 plus Ka into A into 1 plus K into Kb. This type of reaction is applicable in reaction between hydrogen and nitrous oxide on gold and hydrogen carbon monoxide on tungsten. In case of bimolecular inhibition, the reaction between A and B occurring by Langmuir-Hinsel mechanism and inhibited by gaseous substance on concentration of the inhibitor I. If Ki is the adsorption constant for I, the fraction of the surface covered by A and B are given as follows because it includes the concentration of the inhibitor. Then the rate is going to be given as K into theta A into theta B. If there is a sparse coverage by reactants and large coverage by inhibitor, the equation reduces to B is equal to K into Ka into Kb into concentration of B divided by Ki into concentration of the inhibitor square. Thank you.